All right, so what we'll do here is substitute values into derived functions. But what we're doing is that if I've got an original function of some curve here, and I want to find f dash 3, what I'm actually doing is finding the gradient of the curve at x equals 3, and finding the gradient of the curve at x equals negative 2. All right, so this is what it's asking. It's what is the gradient of the curve, what that would graph to. So to do that, what I do is differentiate this equation, differentiate that equation, and then substitute 3 for x. So the first thing we do is some calculus. And we say, okay, well, f dash x equals, and I differentiate this, just like from the last lesson. Exponent multiplies to the coefficient. 3 times 2 is 6, and I take 1 off the exponent. And I do the same for the next term, which is... Okay, so what that is that's the gradient function. Now what I do is I just substitute 3 in for x. And when I substitute 3 in for x, I substitute into the gradient function. 6 times 3 squared plus 2 times 3. And I get 3 squared is 9. 9 times 6 is 54. And 54 plus 6 gives me 60. All right, so what does that mean? It means that's a pretty steep gradient, first of all. But it means on that curve at x equals 3, the gradient is positive 60. So extremely steep curve, almost straight up. Okay, next one, same steps except it's negative. And it's the same gradient function, so I don't have to differentiate it again because I'm still just using this equation for the derivative function. That hasn't changed. So instead of just substituting 3 in, I substitute a negative 2. 6 negative 2 squared plus 2 times negative 2. And the rest is algebra, meaning just evaluating that expression. Simplify this, this gives me 24. You'd be doing all this on the calculator anyway. 2 times negative 2 is negative 4. And I get 20, I think. Yes. Okay, so that means that at x equals negative 2, that has a steep gradient as well of positive 20. And I think I did all that right. Let me just check. Yeah. Okay. All right, let's just look at some other examples here. So this one, I've got to simplify it before I differentiate it. So I have to do some algebra first. And to do some algebra first, I'm just going to write it as 2 fractions over x, like this. Okay, so there's the algebra I do first. I can write this as an expression of both over whatever that denominator is. And now I can, don't do any calculus yet, just simplify. I can cross-cancel an x there. I can cross-cancel 1x there and 1 up there. So I'll turn that into a 1. Okay, so that's still fine. And I'll rewrite this expression because it's looking kind of messy. I get 3x minus 4. So that is just that expression simplified. All right, now I do the calculus, which this is a pretty easy one to differentiate. That's just constant terms differentiate to 0. So this is just going to differentiate to, remember there's a 1 right there. 1 times 3 is 3. And what does that mean? That means that my gradient function is just 3 no matter what I substituted in for x. There's no x over here in the gradient function. So that means that whatever I plug in, which is 2, out comes 3. Okay, I didn't have to do any substitution like I did this one because these gradient functions have an x in them, whereas this one didn't. Okay, let's look at another example where we've got some negative exponents because those are always fun. Got my original function up here. and I want to find what the gradient is at x equals 1. Before I do anything, though, I need to rewrite this so it has a negative exponent, because I do that first, and that means it's going to be h of x is, remember what negative exponents mean, that's going to be 2x to the negative 3. That's how I rewrite that. Now I can differentiate it. Multiply the coefficient times the exponent, so that gives me negative 6x. Take 1 off the exponent. Negative 3 minus 1 gives me negative 4. And now substitute 1 into that equation, which is a pretty easy substitution. Positive 1 is always an easy substitution. And you'd probably do this part on the calculator, but 1 to the negative 4 gives you 1. And 1 times negative 6 gives you negative 6. Okay, let's look at one more example here. And in this one, what I'm doing is I'm giving you the original equation, and I'm giving you what the gradient is at a certain x value. I'm saying, here's the original function, and where is x going to be if the gradient is 13? So when it's written like this, it's saying what value of x has a gradient of 13? And you're going to have to solve that. So in order to do that, anytime you see this g dash x, you're going to find the gradient function first. All right, so we're going to use calculus, and we're going to differentiate this, which is quite easy. G dash x equals 2x minus 7. Okay, and now what I do is, this is telling me that it's equal to 13. So I set this expression equal to 13 and solve for x. And when I do that, this is a straightforward linear equation. The equation could be linear, it could be quadratic, it could be an exponential equation. In this case, it can't really be any easier. Take the negative 7, put it to the other side. That means 20 equals 2x, and divide by 2, and I get 10 equals x. All right, so in English, on this curve, when x equals 10, the gradient is 13. Okay, let's do just one more example where it's not a linear equation, but like a quadratic equation. So in this equation, I want to find the value of x where the gradient is 0, where the gradient's a flat line. And so first thing I'll do is differentiate it, set it equal to 0, solve for x. So when I differentiate this equation, I get 3x squared minus 10. Now what we do is, since f dash x is equal to 0, I set this equal to 0. 3x squared minus 10 equals 0. So if we had a graphics, we could solve it with the graphics. I don't see any factorizing going on first, so I'll put the negative 10 over there. Divide it by 3. And so right now I've got x squared equals 10 thirds. I'm going to get two solutions because when I do the opposite of squaring, which is square rooting, I've got to do the plus or minus square root of 10 thirds. So if I want to decimalize that, well, I can get an approximation here with the calculator and just write it as a positive and negative number. Okay, and I get my decimal approximation here. If I didn't want to write it like that, I get two different points where the gradient is equal to 0. Okay, and that's just some examples there.